Hello, welcome to my talk on optimizing information loss towards robust neural networks. My name is Philipp and I'm working at Fraunhofer Isaac in Garching near Munich in Germany. So let's start by having a look at my agenda for today's presentation. First, I will introduce you to the research field of adversarial machine learning, and then I will show you an approach to make deep learning or neural networks more robust, which is called adversarial training. In the third part of our presentation, I will introduce you to our contribution, which is called entropic retraining, which is closely related to adversarial training and also increases the robustness of neural networks. Finally, I will conclude the small presentation with a summary and a list of our contributions. So adversarial machine learning, what is this research field all about? So basically in evasion attacks, the attacker crafts adversarial examples. Such examples are slightly perturbed inputs, which leads the attacked neural networks to misclassifications. On the right-hand side, we can see two examples of such adversarial examples. So the left images are the original inputs fed to the neural network, which are classified correctly. In this case, the first image is correctly classified as a plane, and the second image is correctly classified as a stop sign. During the attack, the attacker adds slight perturbations, a little amount of noise, and on the right-hand side, we can see the combination of this slightly added noise and the original inputs. And we can see that the pairs are very similar to each other. So the plane still looks like a plane and the stop sign still looks like a stop sign. So therefore, those adversarial perturbations are often human imperceptible. We cannot see them. But both examples are misclassified in this case. The plane is not classified as a plane anymore, and the stop sign is also misclassified, in this case, as a 100-mile-per-hour sign. And all neural networks are vulnerable to such adversarial examples, and they are very hard to protect against. And why do we even care about this? Well, on the right-hand side, the bottom example, we can think of use cases where this could lead to severe incidents. In this case, for example, in autonomous driving. So if the stop sign is not classified as a stop sign anymore, but as a 100-mile-per-hour sign, this could lead to accidents and also harm the passenger of the autonomous vehicle, for example. So let's talk a little bit about the attack methods. They are usually bound by different norms, by the L2 and by the L-infinity norm, to measure the distance between the benign and the adversarial example. So to ensure that during the attack, the adversarial examples are really close to the original inputs and that the perturbations which are added to the original inputs are really human imperceptible. The attacks could either be black box, white box, or adaptive. So here, in the black box attack, the attacker only sees the input-output relation of the neural networks. And in the white box attack, the attacker also sees or can calculate the gradients, knows the weights of the attacked neural networks. And in the final approach, in adaptive attacks, the attacker also knows potentially use countermeasures and can craft adversarial examples which fool the attacked neural network and also the countermeasure simultaneously. Attacks can either be targeted or untargeted. So the attacker can either just flip the output of the neural network to another class, or he can precisely say to which class the current input should be classified as. Some attack examples on the right-hand side, for example, the Kalini-Wagner attack, which is considered to be the most powerful white box attack, or for example, the one-pixel attack, where the authors show that only changing one input pixel in an input image sometimes is enough to create adversarial examples and fool the attacked neural networks. So what about countermeasures? Here I listed a few examples. I divided the approaches in active and passive methods. On the left-hand side, the active methods, for example, adversarial training, which I will talk about later, or defensive distillation. Those always come at a cost. So there's a trade-off between accuracy and robustness. So if we increase the robustness of our neural networks, we have to pay a price, which is usually the accuracy. So we suffer in accuracy here. So the neural networks are more robust, but they cannot classify as well as they classified before. On the right-hand side, we can see some examples of passive methods. The most prominent example is adversarial example detection, but those countermeasures are sometimes attack-specific and can be often circumvented by new and clever attacks, or of course by those adaptive attacks where the attacker knows the countermeasure. He can both attack the detector and the neural network, and then again can craft adversarial examples. So let's talk a little bit more about adversarial training. So this is an approach which is widely known and long for quite a bit now. Here, the approach is based on a pre-trained neural network, on a pre-trained model, and this model is retrained. So, but in this case, not using the clean examples, but using adversarial examples. And according to Madri et al., the state-of-the-art approach for adversarial training uses PGD as the attack generator in this case, and the training should be iterative, so that you, for one epoch, you generate adversarial examples, train your model, and then you again recraft adversarial examples for the next epoch to train or to retrain your neural network to make it more robust. The downsides of this approach are the computational costs. So you need to retrain your model, which is of course a additional cost, but also you need to craft the adversarial examples, which is often very computational, costly and takes a long time sometimes. Then, of course, what I talked about earlier is the accuracy and robustness trade-off. And one final point is the deliberate choice of parameters and also the stopping criteria. When do we actually finish, or when do we actually stop our adversarial training process is also a interesting question for research. Now let's talk about our approach, entropic retraining. And therefore we need to take a step back and have a look at information theory and information theory in machine learning research. So this is also an active field of research. I listed here 3 interesting publications, but those publications look at deep learning in general and try to figure out how deep learning in general works and how to explain deep learning or the deep learning performance with information theoretic tools. First approaches were made to transfer this knowledge which we gained in information theoretic approaches to understand deep learning or deep learning training. Those approaches are transferred to adversarial machine learning. For example, Terzi et al. This year, so it's very recent, they introduced the following idea or the following observation. They made the following observation that adversarial training reduces information and improves transferability. So in our experiments, we wanted to have a look at this phenomenon, at this observation. Why or what actually happens during adversarial training and how is the information actually reduced? So therefore we introduce these values here, which are inspired by Terzi et al. So we were inspired by this publication. We wanted to also have a look at the information theoretic effects of adversarial training on neural networks. And first, let me introduce you to the Shannon entropy, which is a measure for the information. And the information, the Shannon entropy takes probabilities as inputs to this formula. But here in this paper, in our experiments, we directly use the activation values of the neural networks to calculate this so-called activation entropy. So note, from now on, when I talk about entropy, I refer to this activation entropy, which is not the entropy in the classical sense, but here adapted to our constraints in this paper here, that we directly use the activation values as inputs to this Shannon entropy formula. And on the right-hand side, I will introduce you to the 2 metrics, or the 2 values which we use in our paper, which is the mean network activation entropy and the network transition entropy, network transition activation entropy, EN and ET. So EN is based on this activation entropy, and it's normalized. So it's calculated for each layer and normalized by the number of neurons, and then we calculate the mean over all layers. So EN is actually the mean network activation entropy of the analyzed neural network. The network transition activation entropy, ET, is calculated as the distance or the difference between the activation entropy of the first layer and the last layer, so we can get an intuition how the activation entropy changes throughout the neural network during forward passes. So based on those 2 metrics which I introduced earlier, this ET and EN, we made first experiments with adversarial training, and we wanted to see how those 2 values actually react to adversarial training. So let me introduce you to our experiment setting here. We performed experiments with the MNIST dataset. We pre-trained a target neural network based on the LeNet 5 architecture, And later we performed an attack on this adversarially trained neural network using FGSM. So what is the first observation of our experiments? Well, we trained the neural network, or we adversarially retrained the neural network for 200 epochs and attacked multiple instances of this neural network with the FGSM attack method. So on the x-axis, we see the epochs we used, or we trained the neural network with adversarial examples. And on the y-axis, we can see the attack success rate. So the first observation is, we know this from related work. We know this from state-of-the-art that adversarial training indeed increases the robustness. So at the point x, so at the x point of 0, so no adversarial retraining, we see that the neural network is very vulnerable to adversarial examples. So the attack success rate is very high. But the more epochs we train, we perform adversarial training, the less or the more robust the neural network gets. So the first observation here, adversarial training increases robustness, which we know from state-of-the-art research. But now let's have a look at our metrics, which we introduced earlier, EN and ET. And we make on the left-hand side one interesting observation, EN, which is the mean network activation or activation entropy. This EN is reduced in the course of adversarial training, which is very related to the findings by Terzi et al., where the authors state that adversarial training reduces the information in the neural network. Again, note EN is not directly a measure for the information in the neural network. It's related to the information, but it's again directly calculated with the activation values in this case. And on the right-hand side, this transition activation entropy increases in the course of adversarial training. So the more we perform adversarial training, the higher this ET gets. So our concept in this paper was to use this observation, to use our metrics, which we introduced earlier, and try to mimic the effects of adversarial training. So what does this mean? So the optimization goal during adversarial or during entropic retraining is to increase ET and to decrease EN, like it happened during adversarial training. And we try to accomplish this only by using the original input. So we do not craft adversarial examples. And again, we use a pre-trained target network or pre-trained model like it is done in adversarial training. So on the bottom of the slide, we can see the loss function, which we used during our training approach. And we can see that it consists of two components. So the total loss function consists of the normal loss, in this case, the sparse categorical cross entropy, which is just a measure for the performance of the neural network, so the classification performance. And the second term is a measure which quantifies distance of our currently measured ET compared to the ET which we want to optimize towards. So we want to increase our ET. So this in this term, the distance is calculated such that the loss gets higher the more we are away from our target ET. So we want to increase ET. So here, similar to the previous experiment, we performed entropic retraining for the same amount of epochs. We performed adversarial training just to preserve this comparability here in this case. And again, we plotted EN in ET with respect to the number of epochs of entropic retraining. And interestingly, we can see the same effects as we saw during adversarial training. So EN decreases, similar to the observation by Terzi et al. Not only adversarial training decreases EN, but also entropic retraining decreases EN. And similarly, ET is increased during entropic retraining, as this was our optimization goal, as this was part of the loss function which we used during entropic retraining. But more interestingly, what happens during attacks? And here again, on the x-axis, the number of epochs during entropic retraining, and on the y-axis, we can see the attack success rate during the evaluations. And we can see that the attack success rate significantly decreases in the course of entropic retraining. And therefore, we made the observation that entropic retraining, similar to adversarial training, increases the robustness of neural networks, but in this case, without the generation of adversarial examples. And we wanted to confirm this initial observation with a wide range of experiments. We performed those experiments before different neural network architectures, for 3 different data sets, and for in total 5 attack methods. And we again measured the level of robustness by measuring the attack success rate for fixed distances between the benign and adversarial examples. And here, if you want to know more details about the experiment, please have a look into this paper. Here in this short presentation, I can only add the main results, which is this table here. So we see the attack success rates after entropic retraining. And please note that for the initial neural networks, which are not retrained with entropic retraining, those attack success rates are close to 100% for all attack methods. And here in this table, we can see that we could significantly decrease the attack success rates and hence increase the level of robustness for the 4 neural networks. So the conclusion here is entropic retraining increases the robustness of the analyzed neural networks. In the next experiment, we wanted to see if there is also a trade-off similar to adversarial training, where we optimize towards robustness, but lose a little bit of performance regarding the accuracy of the neural networks. And here in this case, we partially can confirm this observation. So on the left-hand side, we can see the performance of the neural networks, of the pre-trained neural networks without entropic retraining. And we can see on the right-hand side, after entropic retraining, that the performance of the neural networks slightly decreased, but not to a very high extent, so that entropic retraining does not significantly reduce the performance of the neural networks, and also preserve the stability towards noisy inputs. So those inputs where we tested also the robustness towards noise, random noise, so that we can see that the models could still be used in the field and are not just robust but not performing at all and also vulnerable to noise. We, in this case, could confirm that entropic retraining does not significantly reduce the performance. So to have a better feeling of entropic retraining, what does actually happen in the neural network during entropic retraining, we performed additional evaluations for an additional analysis of entropic retraining, and we calculated the network activation variance. So the variance of the activation values in the neural network, the mean network activation variance, without the input layer. So we just looked at the dense layer and the output layer and calculated the variance. And we can see that in the course of entropic retraining, this variance significantly increased in the course of entropic retraining. And why is this the case? Let me introduce you to our heat maps, which we calculated. So on the left-hand side, we can see the heat map for normal training. And on the right-hand side, we can see this heat map for entropic retraining. What do we see in both images is that for one specific layer of the neural network and for one specific input class, we calculated the activation values and plotted them here with a heat map. So the brighter the colors are, the higher the activation values. And interestingly, on the right-hand side, the more entropic retraining we perform, the more confident the neural network is for each class. So in this case, we performed this experiment again for the linear target model and the MNIST data set, and in this case for the class 5. And in this specific layer of the neural network, we can see that only a small amount of activation values are significantly higher compared to the rest of the activation values during entropic retraining. So the activation values reach values of over 50 compared to normal training where the maximum value is around 6. And on the left-hand side, during normal training, more activation values are closer to each other compared to entropic retraining, where a small amount of activation values are much higher compared to the rest of the activation values. So let's summarize entropic retraining. What did we see? What are the takeaway information? What the takeaway messages here? So entropic retraining only requires a pre-trained target model and only uses normal training data without the costly adversarial example generation. Entropic retraining increases the robustness of the neural networks by mimicking the effects of adversarial training. So by also increasing the network variance, and also enforcing a very confident prediction of the neural network, which is also related by different findings, for example, here by Chubbuck et al., it's closely related to the prediction and entropy regularization. What are the future steps which are required to further understand entropic retraining and maybe also improve it? Is that we need to take very specific information or very clean information theoretic approaches and analyze adversarial robustness and adversarial training. So here we introduced EN and ET, which are slightly changed compared to the original ideas by Shannon of the Shannon entropy. And we need the true information theoretic tools to analyze entropic retraining and adversarial training to understand what actually happens on an information theoretic level. What's also interesting for future work is that entropic retraining could also be combined with different countermeasures, with different defense strategies, for example, also with adversarial training to allow an even more robust training approach to protect neural networks. So let's conclude the small presentation. We analyzed adversarial training using information theoretic inspired metrics. This analysis is based on this analysis, we propose entropic retraining, which is an approach to make neural networks more robust without the costly generation of adversarial examples. And with entropic retraining, we empirically show that this approach significantly increases robustness of the analyzed neural networks. So thank you very much for your attention, and I'm really looking forward to your questions. Thank you very much.